So following on from this introduction, thank you very much for covering it. It was good to hear that there is also an effort toward having more funding for innovation, because with Sustain, we actually work on bringing state-of-the-art innovation into decarbonizing steel. I think among all the work done within Sustain, I am the less directly and immediately connected to steel, meaning that I'm actually working with CO2 primary. And obviously, as we just heard, CO2, it's connected with the steel making, and that's the reason why I'm here today morning to present this material to you. So the title of my presentation is on the first slide, and the presentation is divided in two parts. The first one, it's related to carbon emissions in steel. I don't want to spend too much time, but I thought having this chance to be the first one on presenting on the 2 days, it was also a good idea to put a bit things into context. And then I will talk about electrolysis and the role of electrolysis within steel making, and what are the ideas for the future. The lead of the task in which I work and I actually implement is Professor Andrew Barron, who is working with me on this work. Right, so let's start. I have to say, first of all, this is a high-level presentation. I'm not going to bog down yourself into technicalities and put you to sleep. So at the very start, the UK industry, as we just heard from UK Steel, in the UK is producing around 3% of greenhouse gas emissions. This value is higher globally. It's around 7%. This number comes from the World Steel Associations. There are several numbers going around between 5 and 9. However, the point here is really a very big slice of the CO2 emission worldwide. And here in the table, we see the conventional technologies that are used to produce the vast majority of steel worldwide. So we heard about the blast furnace, basic oxygen furnace, and then electric arc furnace. The point I want to make here is that depending on the type of technology, we have anyway emissions of CO2. The largest for blast furnace, it's around 2 tons of CO2 per ton of carbon steel. The average value is around 1.8 of all of these ton of CO2 per ton of steel. And electric arc furnace, starting from scrap, so from iron that it's already reduced, uses less CO2, but still there is some emission. And this DRI, it's a direct reduced iron using natural gas and electric arc furnace then to melt and proceed with the process. It's still emitting a significant amount of CO2, between direct and indirect, 1.4 ton of CO2 per ton of carbon steel. So the point here is that steel is using a lot of coal, natural gas, and it's a large user of electricity. And because of this reason, there is a necessity to use this CO2. This is a simplified representation of a generic integrated steel plant. Obviously, we are not going to do through all these details, also because I'm not surely the person who can describe you how the steel plant work. But I want to show you that in a blast furnace process where all gases are integrated, we have emissions directly in the environment of CO2. These are the concentrations, but also we have a large amount and volume of gases carrying CO2 or carbon in the form of carbon monoxide all around the plant. So what we can do here is to work on decarbonizing, capturing CO2 from the emissions, or trying to decarbonize the process gases. In blast furnace process, roughly between the emission from the blast furnace and then the flared gases, we have 1/4 of the CO2 emitted, and a large amount comes also for the power plant. So this roughly, again, and I'm sure there are experts that knows way more than me online right now, I would say that half in a blast furnace process is connected between generating power and reducing iron ore with coke. Okay. So how is it, and this is based on a search I've done on the literature, how is it that the steel manufacturing is being considered for decarbonization today? A lot of work is related to post-combustion, also because we have a legacy of technologies coming from sweetening of natural gas, for example, on stripping CO2 from acid gases. However, recently there have been work on using what is called vacuum pressure swing absorption, and some of the work we do within our task is also related to carbon capture with the PSA. And this work is also then connected to using oxygen directly in the blast furnace with what is called the oxygen blast furnace. This technology, by recycling the gas after carbon capture, would allow possibly through this process to reduce the carbon emission from blast furnace by a value between 50 and 90%, which is obviously a very large number. I'm not aware if there are any demonstrators of this kind of these numbers are based on studies and simulations, but there is a high potential by introducing these to reduce emissions at a cost. Unfortunately, carbon capture has always linked the cost, and as a matter of fact, right now, the cost of carbon allowances is still lower than to deploy carbon capture, and this is keeping, let's say, the development and the application of the technologies ashore. And so, starting from this, I want to move now to the part of electrolysis. So we just saw that there is interest on a post-combustion approach. However, other processes that are emerging are related to using power that is not connected to fossil fuels. And this power, it's renewable energy. Obviously, we need a large amount of this. So this is very much connected to the deployment of enough of this energy. But assuming that in the short future, in the next 10, 15 years, we have enough renewable energy, this energy could be used in a series of processes. I don't want to spend too much time on this diagram, but what I want to show, there are ideas and technologies connected, emerging technologies, so they are low TRL, related to reducing iron oxide directly to iron using electricity. Another one is the CO2 electrolysis, the topic of this presentation, and the other one is water electrolysis. The water electrolysis is generating hydrogen. We know that hydrogen is a source of energy and a reducing agent. It's being considered for direct reduction of iron ore to steel, and it can be used in other forms to generate syngas. So the focus now on my presentation is on this step. I want to give you an idea of how CO2 electrolysis can be integrated, and it's very high level, into steel making process. So this is the OSEC, which is the SOC, sorry, the solid oxide electrochemical cell. This electrochemical cell has been developed to date at the TRL 8 and has shown to be stable for about 1 year. However, if we look at all these aspects of the process, we see our blast furnace here loaded with iron ore and with coke, and the process is happening. We then take the blast furnace gas. Carbon capture allows us to create a source of CO2 that is then fed into this electrolyzer. The electrolyzer generates then syngas, which is then fed back directly into the blast furnace, where carbon monoxide can work as a reducing agent, so should be displacing the amount of coke necessary to reduce the iron ore. And at the same time, also this solid oxide electrochemical cell can generate oxygen, and the oxygen can also be used directly, as I told you before, from the oxygen blast furnace. And the point I want to focus your attention on is on the right-hand side here, where in order to run this specific cell, we need the renewable electricity, as I told you before, because we are using now electricity to do CO2 electrolysis, but especially we need a large source of heat. These systems operate between 800 and 900 degrees C. They are very efficient. However, their operation is at increased temperature and also in some cases at decreased temperature. So it would be good from this point of view to try to think of a process where we eliminate the need of this extra energy. And that's where the work we are doing Sustain comes in, with what is called an alkaline electrolyzer, where the goal at this point is to take CO2 and electricity directly, operate at room temperature and pressure, and possibly generate a syngas. However, the very good point of using alkaline electrolyzer is that besides generating syngas as not efficiently as a solid oxide electrochemical cell, they can generate a plethora, a very large group of different chemicals. This then links the steel production to the chemical industry and the production of chemicals, where we would have to think about integrating the two and find a way on a larger picture and approach on how all these products generated from this alkaline electrolyzer could be then joined into the chemical industry, which needs to be defossilized as much as the steel industry. I'm checking my time. Okay, so the idea I'm proposing in terms of Sustain is that on top of the different technologies that we saw before and approaches, it's a direct CO2 electrolysis to chemical products. Now, on a very high level, I want to tell you what we do in Sustain. We operate at TRL 1 to 3, so we don't have a TRL 8 as I showed you before, which is available. We have one postdoctoral researcher working on several aspects of electrolysis. We work on the fundamentals, where you can see some molecules here. So we really work to simulate how these work on our catalyst. We design different electrocatalysts that facilitates the reduction of CO2 to those products I showed you before. We then go to what in our lab we call a larger scale, however, it's still a bench scale, to develop gas diffusion electrodes. There are specific electrodes that use CO2 in the gas phase to achieve current densities that are of interest for industrial scale-up. This is an example of the electrode that on which we translate our fundamental study to a larger scale. And then this is all the system that we use to develop this system. So now, this might be a bit surprising to most, since, as we just heard, by 2050, the idea is to defossilize and decarbonize entirely the steel industry. You wouldn't start from this system. So what strength and point can I highlight from this point of view? I can tell you that based on the work we do, which is leading at world level, we are really designing catalysts that are able to selectively produce those materials. For example, we went to the synchrotron in diamond, where our electrochemical cell was in line to this beamline, specific beamline, and we have been studying what are the chemical species forming on the electrode and how we can govern the electrochemistry on the surface. So this is very fundamental. But then we moved on also on with pioneering work, modifying this foam with polymers to enhance the production of ethylene. Ethylene is this C2H4. So our interest is in producing ethylene. This would be the defossilization of what we call petrochemistry. And from this work, a work then came after in the US just very recently. So this is not really ours, but our work, it's cited. Now, the efficiency of conversion of CO2 to ethylene has reached 90% with energetic efficiency of 50%. So we are getting very close to the performance of the system I showed you of solid oxide electrochemical cells. So this is my last slide. I want to show you a little bit of what we have been doing. We have been preparing different micro nanostructures of copper electrodes, where we can really control at the nanostructure level what species we can form. Each of these species have a different catalytic activity. We can translate this on a net of copper metal. So these are self-supported gas diffusion electrodes. We have successfully made them hydrophobic to be able to operate on the right-hand side here. You see our gas diffusion electrode operating and generating gaseous products that we are now collecting. So the next step in this process is there is globally an enormous amount of work in this field. However, there are two key aspects that need to be approached. One is called the carbonation problem, which is related to the energy efficiency of the system. And with our PDRA, we are looking into it. All world is looking into it. And the other one is the impact of impurities in the gas stream on the overall system. So we are working at this level, as you can see. However, together with us, there are many other experts in the world. We are moving forward with this technology. And probably my last message is we would really like at the workshop of today is to come into contact with other people with this expertise and possibly to funders who can follow up to the work on sustain and allow us to scale up this technology and help the steel industry to decarbonize. So with this, I finished my presentation. I'm not sure if I'm over time, but thank you very much for listening. Thank you.